we've been talking about contaminant transport exclusively. I was going to say predominantly, but exclusively. But most importantly, what we've been talking about is what we'll refer to as conservative transport. Not in a political sense. And that merely refers to the fact that the mass of solute that's present within the water that's flowing is conserved. It's always left in the solute. It'll move around as the front advances, but it's always left dissolved in water. Non-conservative solute transport is when a portion of it is removed to be immobilized, if you like, on the grain boundary, on the grain faces. So it sorbs onto the grain faces, is therefore lost to flowing downstream, and therefore, by definition, is non-conservative. And so what we'll talk about is trying to understand that behavior. Last Thursday, we spent a bit of time at least making the case that the residence time distribution curves that you've already used for Longstreet in assignment 1, for instance, aren't quite correct. We'd always assumed that if you look at the residence time distribution, this breakthrough would occur at some time which is given by one pore volume of fluid coming through the system. And that's certainly true for advection-dominated flows where you have this plug flow front that moves through and therefore will arrive all at one time. Furthermore, we always kind of assumed that if you have a little bit of dispersion around the front, then the effects of that is that you'd have an arrival time which would arrive earlier than it should do based on plug flow, and it would continue to break through later than the immediate plug flow, but that the average time, the time of average concentration, say 50% C over C0, was roughly at the center of mass of the plume, and therefore would refer to this one pore volume breakthrough. It turns out that if you have highly diffusive flow, where the advection component is very small, and hence the Peclet number, which is given by a flow velocity, a characteristic length, and a dispersion coefficient, DL say. When this amount is large compared to the velocity, so this term is less than 1, then all of a sudden this point when breakthrough occurs becomes progressively earlier and earlier in terms of measured by pore volumes. It won't be earlier and earlier in terms of real time, but if we normalize behavior in terms of pore volumes, then if a Peclet number is, say, 0.1, then maybe it occurs after only 2/10 of a pore volume going through. It doesn't mean that it gets, see if we can get through, that's for the pad. It doesn't mean that physically in time it'll arrive earlier, but it will arrive earlier in terms of pore volumes. Physically in time it'll arrive later because the number of pore volumes that you're filling with the advective flux is almost zero, right? In the limit for diffusive flow only, the number of pore volumes will never reach 1 because it's not flowing, it's just diffusing. And so that's one thing that we have to accommodate. So that's a useful thing for us to be able to understand. So clearly in this, then, for conservative transport, we would like to know what the value of this dispersion coefficient is, which we think is equal to something like diffusion plus a mechanical dispersion coefficient longitudinally times the velocity. So this is molecular diffusion, Brownian motion. This is mechanical mixing, as we've talked about, in terms of these different flow paths that mean it spreads as it goes ahead. And we'd like to know what this is. Clearly this is something that we need to know if we're going to calculate what this arrival profile will look like. And so we could go into the laboratory and run an experiment where we put some stuff upstream, flow some water through the core, and measure the behavior downstream. And that may or may not work. It will work if it's diffusion only. So if it's diffusion dominated, that works pretty good, pretty well, because diffusion acts nicely in these pores and goes downstream. If it's advection dominated, then it turns out not to work very well. And the evidence of that is given in this one figure, which is in here, which would be in the stuff from last on Tuesday, which you'll see, is this graph here, a key graph. And what is plotted here is that on the bottom axis it has the scale of the measurement. So you can think of this as being the size of the plume. And it goes from 1 kilometer to 10 kilometers to 100 kilometers. Big regional sized plumes that have been happening over geological time. Bless you. And the magnitude of this dispersion coefficient, which goes into this parameter, molecular diffusion plus dispersivity times the advective velocity, this term here, which is in units of length, varies also as a function of the scale. And so you can fit a curve through this. There are big limits on it, upper bounds and lower bounds, and you can draw a reasonable curve, I guess, that goes through the middle of this, which is this. And the curve for this is something like alpha L being equal to the length of flow, which is this, the scale, divided by some number, 10, which is curious, right? It's not so it doesn't matter if it's clay or if it's gravel or sands. The material doesn't make any difference because these are a whole bunch of different geological environments, but it seems to relate only to the scale of the measurement, i.e. whether it's a plume that's gone. That's not very good. Let me do this again. In other words, it's a plume that's gone this far, in which case the length would be small, or a plume that's gone this far, in which case the length would be larger. And that seems to make no sense until you think of what this could mean. And basically the interpretation of this is that as you get to be a larger and larger plume, the chance that you intersect some big flow feature like a fault or a big fracture becomes increasingly larger because the volume of the plume is larger. As you get even larger, then the feature that you can intersect now is maybe a regional scale fault, which allows you to get some really fast flow in one portion of it and really slow flow in the other, and therefore the spreading increases. The coefficient describes this, the spreading increases. So that's largely put down to the fact. So this is kind of a curiosity, but basically this is this value of L divided by 10, which goes in here. So it's not a constant throughout the life of the plume. It depends on as it develops. So that's kind of a curiosity. And so that points to the fact that running an experiment in a geometry that looks like this is probably not very good for us. These so-called laboratory experiments. Because one, it's a very small sample, it can't be a big one, and it doesn't incorporate this intrinsic behavior that is this heterogeneity. And a much better way of doing it, and an example that you'd see if when you look at the video and do the quiz, is that one way to do it is so-called natural gradient tracer tests. And natural gradient tracer tests are what they suggest. It's flowing under the natural hydraulic gradient that's present in situ. And so you put a bunch of stuff in the ground at point A, down at the bottom here, and you wait for 85 days, and you go and look to see where it is, and then you wait for a year and a quarter, and then for 2 years, and you go and hunt down where it is. It happens to be pretty easy in this case because the geological environment in which this was done, it was done at Borden Canadian Air Force Base in Ontario, is by putting in little capillaries into a sandstone aquifer, into a beach basically, and sucking out water and looking at wherever you sample it to see what the concentration is, and to be able to look at what the concentration rings of this plume is as it goes down gradient. And so what we can do is if you can define at a particular time, if you can define exactly what the size of this plume is, in terms of, I suppose we could draw a little figure that looks like this. It's upside down. But the concentration that's in this plume is going to look like this, right? This is this normal distribution curve. And we know that this is this one portion here is equal to 3 standard deviations. And we know that 3 standard deviations are equal to this term here. 3 times square root 2 dxt. So this is, well, I can write it out. So 3 standard deviations, I'm just writing out this term here, is equal to 3 times the square root of 2 times the dispersion longitudinally in this particular case, times the time since it was initiated. And so in this we know that the time since initiation happens to be 85 days. We can measure this length here because it's a physical length, which is whatever it is. You could just scale it off here. And so as a result of that, we can get this value here. So we can solve for this dispersion coefficient. If we know what d sub L is, we also know that this is equal to diffusion plus this longitudinal dispersion coefficient times the velocity. We're going to assume that this is 0, this Brownian motion part. We assume that we know how far it's taken to go 9.5 meters in this particular case. And if we know how long it's taken to go that far, then the one parameter we can calculate, we can also get this from this. The one thing that we can get is this dispersion coefficient. So that's how you go about getting the data that appeared on that shotgun blast on the barn door for that length versus alpha L plot that we just looked at, that had a gradient of 1/10 of the length of the plume defining that behavior. So that's how those individual data points are gathered for that particular plot. And usefully, that plot tells us that this magnitude should be equal to the length of the plume divided by 10. And we could check that in this particular case. So that's kind of a recap of what we would have talked about had we been here on Tuesday. And so we'll leave it at that. Bottom line is, to get this aquifer scale dispersion, you need to do probably experiments that exist at that scale, otherwise you're way off. And also, some part of it is helpful if you do it under the same gradient that's flowing in this. So you've dumped this stuff into the aquifer, and it's just happily flowing at the same conditions that it's flowing at already. You're not pumping it in, you're just putting it there and allowing it to be carried down gradient. And the reason for the dispersion, of course, is that you get these high-speed conductor zones and zones that don't do that. And so if you look at the distribution along this front, you'd expect that it would look something like So if you take an average across this front, then that one-dimensional profile is what comes out of it. So hopefully pretty straightforward. And the net impact of that is that these behaviors are controlled by dispersion. So everything up to the end of 3.3 is talking about so-called conservative transport. And so now we'll talk about the case when that's not the case. And we'll look at the behaviors that contribute to 2 effects, retardation and attenuation. So retardation means you're late, it's retarded, gets there late, and attenuation means that it gets there at a concentration which is lower. And so the mechanisms that contribute to this are sorption of the mass onto the solid substrate. And so typically when we take the behavior of an aquifer, we suck the fluids out, we measure the concentrations, and if part of that mass has been put onto the aquifer, then we don't see it because it may be upstream from where we're currently sampling. And so that's the issue that we're dealing with here. And so we'd like to be able to look at what we'll refer to as non-conservative transport. Okay, and it's relatively straightforward. I am going to just draw some pictures, I think, rather than do this, just because I feel like, not that this is monotonous, but I feel like breaking the monotony. So let's do something for change. Okay. And so, yeah, okay. You need time to actually write it down if you wish, but kind of absorb it, right? So that's the whole educational process here. So, if we look at conservative transport, first of all, then we know that the expression that we've been dealing with has been something like, and we've talked about it a number of times, the advection dispersion equation. And it has components that relate to concentration transport due to dispersion-like processes and advection-like processes. So we've seen this expression before. This is advection, this is dispersion, and this is accumulation. So those terms all act together. Dispersion and advection together, I guess, are really mass in minus mass out. So it is a conservation equation that says that mass in minus mass out has to equal the accumulation in a very basic sense. And I suppose if we wanted to draw a picture that represented that, then it's a bucket of grains that has some fluid come in and some fluid go out, but it's not really the fluid, it's the mass of the solute that we're interested in doing the balance over, because it's concentration. And that's the expression that we've used so far. And so it turns out that what we could do is we could add an extra term to this, and you should take it on trust. And this term is going to include the bulk density of the aquifer, the volumetric moisture content, of the aquifer. And so that is, normal density of an aquifer is 2,000 kilograms per cubic meter. Theta is the volumetric moisture content. So it's actually equal to the porosity times the saturation of water. So if it's 100% saturated, it's equal to the porosity, which we've called N, and multiplied by the change in concentration with time. And so in all of this, the concentration, although we've never said it, is its mass per unit volume, I guess, in solution, aqueous solution, right? So it's mass of sodium chloride in volume of water. So 10 grams per cubic meter of water, or per liter of water, whatever you use. So this is written homogeneously in terms of that. However, I lied. And this term here, this concentration here, is in terms of the mass that's present on the solid. So C star is the concentration on the solid. And so that's fine, but we realize that the term that we're trying to solve this equation in terms of, the concentration in the aqueous solution, is no longer homogeneous. And so what we can do is we can play some games, and we can multiply top and bottom by the change in concentration, which should be just multiplying this by 1. And if we do that, then we should be able to take this, we've done this often, right? You must remember these games that we play. And we can rewrite this equation, as I will write it down below, as a rate of change of concentration with time, which is equal to the dispersion term, second order partial with respect to x. X is down gradient. Advective velocity times the first order change in concentration with length, plus this term, which is some coefficients. And I'm just going to rearrange it in terms of these two parameters here. So I'm going to write dc star over dc, the term that was in this part here, and then multiply it by the term that is present in the rest of the expression. This is time. And so the utility of doing that now is that all defined in terms of concentration, C aqueous, I guess. So that's what we've attempted to do. And it's not very difficult for us to take this term here, which we've newly defined, and take it over to the other side. And so this will become 1 plus this term here. And so we can just rewrite that as bulk density of the aquifer divided by volumetric content, change in the amount that's sorbed onto the solid divided by the amount that's in solution. And so that just gets rid of this term. And so what we have now is kind of a nice little expression, which is a bit like what we had before. And we'll call this term here the retardation coefficient. Which we'll call R. Which means that we can just write this expression as something like rate of change of concentration with time is equal to d sub L second partial minus the first partial. So nothing different from what we've seen before. But now this is pre-multiplied through by this retardation coefficient. And retardation has to be greater than 1, less than infinity, I guess, right? So it has to be, since there's 1 in here, and it has to be finite, we could imagine, I guess we haven't proved that yet, but retardation has to be between 1 and a big number. And so physically what, we don't know how to do that yet, because we haven't figured out exactly how to get this. Maybe we should talk about how to do that. So the easiest way to think about that is to think about what this term is. And I guess the easiest way is to think of an experiment. And so we can define the sorption amount. And sorption is an equilibrium process. And it's pretty simple. The experiment to look at it is to take a bunch of grains in your aquifer, just like we alluded to before, to put in a concentration of fluid and measure what the concentration is that gets sorbed onto the grain somehow. So in other words, put some fluid in. Easiest way to do it is to put in a given concentration of fluid as it goes in, measure the concentration once it's sat in equilibrium with the aquifer to see how the concentration is reduced, and then the amount that has sorbed onto the grains must be the difference between those. And so in a physical sense, I suppose what you'd do is you'd plot for this experiment something that looked like concentration C star as a function of time, and you'd expect it to look like something like this. So if you put in some concentration C1, then the concentration on the solid, if you calculate it, so it's in aqueous solution, it's in at some given concentration at a number, and I suppose the initial C1, I don't really want to complicate matters, the initial C1 would be this number here, right, maybe? And because it gets sorbed onto the solid, it would end up being less than that, because some of it is removed from solution. So this would be the solution, and this would be the solid. And so this would really be C1, but this would be C1 star on the solid. And then you'd go ahead and you do it again by using a bigger concentration. So you put a different concentration in, originally C1, then you do one that's C2, and you measure the behavior again. And this is the same behavior as before. This would be C2, and this would be C2 star. And so the only important thing here is the one that we're interested only in the steady state behavior. So at some level, after some amount of time, it doesn't change anymore. And so what we could do is we could plot another graph directly from this. And this graph would be, again, the concentration that's present on the solid, but versus the concentration on the aqueous. And I suppose we'd be interested in C1 rather than C1 star. So this would be C1. This, I suppose, let me do it fine. This is, I guess this is a bit too simplistic. This would be C1 star. So that gives us 1 point here. And this would be just going to make sure I can do this properly. And so these would be our 2 data points, right? And this would be C2 star, C1 star. So these are the original aqueous solutions. So these would be the flat lines here, nothing else. And so just by looking at this term that we have here, this term here, so rate of change of concentration on the solid versus rate of change of concentration in the liquid is the ratio of these two. So this would be dC, and this would be dC star. And so this curve here would be equal to what we'll call KD divided by 1. This is 1, this is KD. And KD is simply called the distribution coefficient. And so I suppose the important thing to note is that we have an expression here that includes a terms of the physical processes, and that is putting an aqueous solution in contact with a solid, seeing how much gets attached to the solid relative to the solution that's there. Then we come up with this curve of these two. And actually, I suppose it really would be not the value here, but it would be the equilibrium concentration that is there. So that's so C1. I should probably make that. C1 and C2 are equilibrium concentrations, not the initial one, not the initial aqueous. Because it's an equilibrium behavior. It starts off with a bit more in it, some of it gets taken out, so it has to reduce, and so it's the equilibrium between the current concentration within the liquid, whatever that is, relative to the concentration that's on the solid. So the difference will be small, I think, because sorption magnitudes are small, but that's probably an important point. So we get a value of K sub D, which means we can always define this retardation coefficient. So R is always going to be equal to this value 1 plus density of the aquifer, volumetric moisture content of the aquifer, and distribution coefficient. And it's always between 1 and a big number. But we can get it. We can measure it in the lab. We might be able to measure it in the field as well. I guess we'll talk about that. So that's a key point. So that's the first part of understanding the behavior. I suppose the next part is to figure out what influence we could imagine that would have on the flow field, right? And so if you think about that, yeah, it's fun to do it this way. So influence of retardation and attenuation on flow field. And you remember these geometries that we've looked at before for flow along the floor, being a good enough indicator of the system, and looking at transport. We talked about vector flow from point to this. This is rotation. This is relative concentration. We talked about inputs that system we know. Oops, not that. It'd be something like this. This is time, and the output from the system would be something, again, with respect to time, and C over C0 would be something like this for plug flow. And this would be some length along here. All right? And so that conforms to this expression that we've defined, which is the advection diffusion equation with the two components. I'm just going to write it out again so that you're sick of it, but you'll remember it. And it's important to understand what the physical components mean. So now we have this term attached to it, which is retardation. So no longer, it was 1 on this left-hand side, right? It used to be just 1, but now it's a number that's different than that. So what we could do is we can divide both sides through by retardation coefficient. I'm just going to change color. And so if we do that, now we've returned this side so it's equal to 1. And so it's our old retardation diffusion advection equation. But now we've modified these parameters by dividing through by a number bigger than 1. And so because we know why this plug flow pulse and its arrival look like it the way they do, we could surmise that we know what this behavior would do. So the two things that we could imagine. The first is that this will tend to, so R greater than 1 will reduce dispersion, because dl over r is less than dl, right, if r is greater than 1. And it will reduce advection. Because V advective divided by retardation is less than just V on its own. So this is non-conservative versus conservative, right? These two behaviors. So the conservative system, we had just these terms on their own. The non-conservative system, they're divided through by a number greater than 1. And so we could figure out exactly what that would mean. So what does that mean in terms of reducing dispersion? Well, it's difficult to draw on this, but I suppose this would be advection only. If we had a conservative, so if we do conservative as green, then conservative, I suppose, would look like this, and it would look like this, right? You would actually join 1 there. Jeez. A bit of eye-hand coordination out of sync here. So this is what the conservative plot would look like. So what would a retarded plot look like? So one is it goes less far. So I guess it would not go here, but it would go less far. So it would have traveled a length which we could imagine would be that this length, what is it? Velocity is equal to length over time. So length is equal to the product of velocity times time. If the velocity it's going at is really velocity divided by retardation, then this would be this. So this would be equal to the product of advective velocity time divided by retardation. If retardation is 1, then you'd get exactly this plot, if we believe this plug flow thing. So that's taken care of the velocity issue. So the question is, what do we expect to happen with dispersion? So it's reduced dispersion. So I suppose if in traveling less far, the behavior would have been like this for conservative species, then if I do it as blue for non-conservative, then we'd expect it to actually, I suppose, look like this. So to summarize, the two features are, one, it goes less far, but it also gets sharper. Right? It goes less far because the velocity is divided through by a number greater than 1. And it gets sharper because the dispersion is less, and so it wants to be a bit more like plug flow with this very sharp front to it. And so the conservative behavior would expect to get, the non-conservative behavior, maybe a bit surprisingly, is that it doesn't go as far, it's retarded, but it's sharpened. The front is sharpened. So kind of surprising that it actually would be a steeper concentration gradient. And so we haven't done any calculations with this other than just make inferences about what it does to this equation. I suppose what would it do on this side? It would mean that this blue curve would be two things. It's traveling less quickly, and so it would be delayed, and so it would be somewhere over here, right? And because it's becoming through closer to plug flow, then instead of looking like the green curve, then it would look more like this. So this, I suppose, would be equal. So yeah, I guess it's worthwhile doing, right? So the equivalent of this equation, so this is the equation we're using. You could argue that we're using it incorrectly from what we talked about before about whether it really represents this differential equation, but let's ignore that for the moment. It gives us the length that it's traveled, and I suppose the time for arrival, if we do this, would be length time is equal to length times retardation over velocity. And so this would be this. Time is equal to length times retardation over velocity. This is advective velocity. So r is always greater than 1, so it means that it occurs further in the future. So those transformations, if you like, all both make sense in terms of the value of r that we expect. And that's it. And so that's really all it is to be able to talk about this. So we can define the amount that gets stuck on the solid, which isn't available to be transported in the liquid part anymore. Because it's removed, it is attenuated, so the concentrations are less. We haven't dealt with that here. I suppose you could make a good case that not only is retardation occurring, it's arriving later. You could also make the case that maybe it should arrive at a concentration which is lower. And so maybe this concentration as it breaks through should be lower because some of it's got attached to the grains and is therefore no longer in the flow field. And so those would be the effects. All right? So what else do I want to talk about? Something, I'm sure, because we've got all kinds of time left. So what we could do is we could now look at systems where these effects are present. So for that, let's go back to looking back at the notes again. And so what we've done is if we look at this, we've looked at what the process of sorption is. This KD property is really an isotherm. It tells you what the concentration should be if you look at equilibrium behavior under different concentrations of liquid in terms of how much gets sorbed onto the solid. We've looked at how we might measure this, at least in situ, in theory. And so now, I guess, in terms of equating this to what happens in the field, how do we reconcile that with behavior in situ? So how do we look at how we might measure this? So that's basically what I'd like to spend time doing. So this is what we looked at. This is distribution coefficients. What we've looked at is a linear isotherm where there's a linear relationship between the solid and the liquid concentration. You could look at isotherms that are nonlinear, that are a power law. You might have heard of them or used them in your other stuff, Freundlich isotherms. We can look at isotherms which have a peak value in terms of equilibrium behavior. So this isn't in terms of time anymore. Remember we drew a picture in terms of time before. Is it here? Yeah. This picture that we drew on the right-hand side, this here is in terms of time, not in terms of concentration of solid versus concentration on liquid, which gives us this behavior. And so when we look back at the Langmuir isotherm, which is this, then this behavior is in terms of concentration space. So what's this saying is that as you introduce a fluid of a particular concentration, then a certain amount can go onto the solid. Double the concentration, so this would be this amount, C1, this is the amount that goes on the solid. Double the amount on C1, then you get roughly double the amount on the solid. Kind of linear, almost linear. But the point is there's some threshold. And so the threshold is saying that once you've saturated all the sites that exist on the grain of this sand, then it can't go anywhere anymore. It's completely saturated in terms of sorption. No more room. And so then it's constant as a result of that. And so very famous isotherm referred to as Langmuir isotherm. So this is a derivation we've done. Maybe this explains things a bit better than I just explained. And that is the the geometry of this self-sharpening plume is that originally it would have looked like this red curve, the right red curve, and if it's sorbing, two things happen. It goes less far in a given time, this amount here, and it also becomes sharper. So these are both non-plug flow behaviors, one of which is conservative, so this is conservative, and this is non-conservative. And so maybe a more straightforward representation of what I was trying to scribble in real time. This is still the relationship that defines the length it's traveled, kind of, and the arrival time is still as we drew before as well. So we can do those things. The other thing that we could do also is that we could also, if we wanted to, use the characterizations that we did before to describe the rate at which it will travel downstream. And let me go back here. So we need to go back 2 periods to the exact expression that I'm looking for. And that is this, which I didn't clear off. And I'm going to remove this just to make it clean. I guess we used that today already. But you remember that the basic idea when we looked at transport in the subsurface could be this core with an upstream boundary condition. If we solve the equation, which is dc dt is equal to dispersion and advection, then we end up with these solutions. If we want to solve for a system which is non-conservative, then we have this term here on the right-hand side. And if we want to just divide both sides through by that term, which is what we just did, we end up with this behavior where this is 1. And so if we want to be able to figure out exactly what the concentration evolution in our system would be when we have a non-conservative system, so this is non-conservative, then we can use exactly the same solutions that we did before, but we'll have to use modified coefficients. And the modified coefficients would be that we'd use an equivalent dispersion, which is divided through by a number greater than 1, 1 or greater than 1, and an equivalent advective velocity, which again is divided through by a different number. So in other words, when we use them in this expression, the numbers that we should use should be modified. So this should now be V over R. This should now be D over R, etc. You get the idea. Just for good measure, I'll do them all. And if you go through and make those calculations, then these expressions that we used before should be exactly the same. And so the Peclet number then is defined in terms of V over R and D over R. So in other words, this would be divided by R and divided by R. So that doesn't make any difference. So Peclet number is unphased. But this pore volume equation is going to be velocity over retardation multiplied by time divided by length. So this will be changed, right? So this will be equal to velocity, time, length, and retardation. And so if you want to use these expressions to calculate what's going on, then you can do that just by changing these parameters. Either changing the parameters in the dimensional equation or in the non-dimensional equation. You can work through. And so look at that. There has been a question on the exam about that needed that. I don't think there is this year. You can probably see the pattern in the exams as you go through it, but you need to figure that out. And so we could get the shape of the breakthrough curves We've already said Peclet number will still have this structure, but I think the scaling on this axis will be different, right, if you have retardation. I think basically what it would do is it would just physically scrunch these curves up, no, expand them, right? You'd have to get more pore volumes through to get them out. So in other words, you had a very high Peclet number instead of looking physically like this. Sorry, if retardation was equal to 2, then I think that's what it would look like, right? That makes perfect sense. You double the retardation, it goes half as far in a given time, and so the number of pore volumes you have to get before it comes out, because you're still flowing at that same advective velocity, it takes twice as long to arrive at the downstream portion. And so we can figure that out. Okay? So that's one way to be able to do this. The other geometry that we talked about when we talked about these was that instead of having a flow which is in this longitudinal migration along a core, you could think instead of a constant concentration that's applied for all time and keeps on supplying, you could imagine putting a pulse in that then diminishes. And then you have this cloud that disappears downrange, if you like. And so we could do that again, and that's useful because if you remember when we talked about how we measured dispersion, it's not very useful to take a core in the lab and measure it on the core. What is useful for us to do is take the measurement in the field because we think it varies with the length of the plume that develops. And so this might be a geometry that we want to use in the field, and certainly we've used it for one case of conservative transport, which you'll see if you go online, which is this. And the question then is, what happens if that transport now is sorbing components? And so it just turns out that the same experiment that here was done with chloride, and so it happens to be a site where there's this aquifer, there's an underlying aquiclude, which means it's all protecting the groundwater underneath this, so the superficial stuff that happens isn't affecting any groundwater resources, so that's why it's environmentally okay and accommodated by the regulatory requirements. But if you do exactly the same experiment with some components which I think were carbon tetrachloride and what else? And tetrachloroethylene. So if you do the same experiment now and you do it with different with all those components included, so chloride, carbon tetrachloride, and also PCE, and you look at the plume after different stages, then for the case of carbon tetrachloride, this is where it is after 2 years, and for the case for PCE, this is where it is after 2 years. So clearly it's traveled less far as we'd expect. So we'd expect, I suppose, that retardation for PCE is greater than that for carbon tetrachloride, which is greater than that for sodium chloride, which I think it was, right? Just because they've gone different lengths. This has gone least far, this has gone an intermediate amount, and the chloride on its own had gone 57 meters. And so it seems that there's probably something that we can do to be able to figure out exactly what the magnitudes of these retardation coefficients are directly from this. And I suppose you'd imagine that it comes from looking at the shape of the plumes. And the easiest way to do it, I suppose, is to draw it on here as we did before. So after 1 year, this plume looks like this in terms of C over C0. And this plume here looks like this. And the point is that this length here is 3 times the standard deviation. This is 3 sigma, 3 standard is smaller here than it is here. You know. And so we can go through a calculation. I won't bore you with it, but you can imagine that you can go through this calculation to say that 3 times the standard deviation is equal to 3 times, I think, the square root of 2 times the dispersion coefficient times time. We can measure this because it's a length in meters. We can know what this is because it's the time since we released it in this particular case, 2 years, and therefore we can calculate what d sub L is. If we know what d sub L is, we can calculate exactly from this. And I guess I didn't quite want to go there. I'm leading you down the garden path. Right? So this has been sharpened, and so this magnitude here is really being divided through by retardation. Right? Where this is 1, then you get this. When this is less than 1, it should have reduced. So the size of this should have reduced. But I suppose the more telling component is that we know that the velocity is equal to length over time divided by retardation. And so if we rearrange that to give ourselves length being equal to velocity times time over retardation, then we can measure the length. If we know how far it's traveled in the unretarded case, we have the advective velocity, right? If we know how long it's taken to get downstream, we have this. And so by looking at the distance traveled between these two cases, we can figure out what the retardation is. And so retardation of carbon tetrachloride over retardation of chloride is going to be equal to I guess I didn't need to do that. You do that as 1 over the lengths, right? So this is going to be proportional to the length of the chloride divided by the length of the carbon tet, hopefully. So if that's right, so this is a number which is large, this is a number that's small, and so this will be 1. And so by just looking at the ratio of these two lengths, and I'm not sure what those are, but in 1 year this has gone 57 meters. In 1 year this has gone how far? 10, 20, 25 meters. So 57 over 25. So not rocket science, just a matter of looking at ratios. So the bottom line, so that you can pull out from the distance it's traveled downrange, you can get the retardation coefficient. And that same retardation coefficient should self-sharpen these fronts by reducing the length of this probably by a factor of 2, pulling it in by a factor of 2, because you're just reducing this length by that. And I think this calculation is just doing that. And I suppose finally, if you wanted to, if you know that the retardation coefficient is equal to 1 plus the bulk density of the aquifer divided by the volumetric moisture content times Kd, then you know this, you know this. This doesn't change very much, 2,000 kilograms per cubic meter. Volumetric moisture content, maximum values of porosity is 30%, say. And so the only unknown you have in this is the distribution coefficient, which you can figure out. Shh. Talk, but just not so I can hear you. Okay? So that's it. And so retardation attenuation. Retardation gets there delayed, doesn't go so fast because it's sorbed. Attenuation is it may end up in a smaller concentration. You can imagine that the peaks of these distributions are different. Lower in this particular case because it's been sorbed, so some of it's been lost in mass as well as being pulled in. And so that's the attenuation. So the concentration that you experience in the water down gradient is going to be smaller. So those are the two effects. It's due to sorption. We can characterize sorption through isotherms, this so-called KD value, which is the mechanism by which it occurs. If we measure KD in the lab, we could figure out exactly what retardation would be and then what the effect would be on a large-scale system. Maybe we don't want to take that route, though, because what we said about the effects of field-scale behaviors being quite different from lab-scale behaviors. And so the other way to do it is, again, with natural gradient experiments, where we measure the plume in situ to figure out what the large-scale transport parameters are. At vector velocity, we should be able to get from where the center of mass is on this in the unretarded plume. That gives us the vector velocity. If we know how far the sorbed case has gone, the ratio of those two give us the retardation coefficient. And if we want to get from that the distribution coefficient, we can. Whether we need to get it is another case in point. We perhaps don't need to because it's just this ratio of retardation that we need to get. And so once we have it, then maybe we don't need to get this fundamental parameter. Or maybe we do, but we can get it nonetheless. And there's an example there doing that. And the final shot in this is to think about, so we've talked about these effects being observations that look like certain things. So we deal with dispersive transport through this advection dispersion equation because mechanical mixing looks like diffusion. We go downstream, we see the plume is spread out. It's not because diffusion has occurred, it's been mechanical mixed to get that. And so the same occurs in this case. We're interested in understanding the mechanisms that contribute to behavior and that give us the effect. And the effect that we see is that the plume, one, doesn't travel so far. Its arrival is retarded over what it would be otherwise. And it maybe counterintuitively self-sharpens because of this reduction in the dispersion coefficient. So it could be that we would see these kinds of behaviors in other systems where it looks like sorption is occurring, but it's not sorption. And so one example of that is this final example, which is looking at fractured rock. And it's just comparing the signals of what this would look like if you went through fractured rock, even if there wasn't sorption occurring. So you can imagine if it's plug flow in a fracture, it will arrive downstream, not much dispersion because it's just traveling in the fracture, and you sample it along its length. Nothing ahead of it, everything behind it, and there's a front here. If you allow stuff to diffuse by Brownian motion into the water that exhibits in the pore space, not sorption, but just by diffusion, then the effect that you get from that will that this front will be delayed in its arrival over the case here. And this isn't sorbing, but it's diffusing into the water, which is pristine in the rock pores surrounding it. And so it looks like sorption because it's delaying the arrival. And if then sorption occurs on top of that by the stuff in the pore space being sorbed out of the water onto the solid rock, then it would further pull this amount back. And so only this one here is actually due to adsorption. This one looks like absorption because it's delayed, but it's not due to the process. And so that's maybe a recurring theme in the kinds of things that we've talked about. And so that's useful in doing that. So it's clear that looking at the arrival times of these, where the solutes are non-conservative, are controlled by this sorption behavior. So retardation is probably an important thing for us to know. We'd like to know if somehow it arrives in a concentration which is less than we expect it to be because it gets sorbed. And so for the systems that we're looking at, which are DNAPLs dissolved in water, it turns out that we can get the magnitude of this distribution coefficient K sub d, I guess I did it as lowercase k, usually I think it's uppercase. This distribution coefficient, we'd like to know how to get that. We can do it through the methods that we just did to get retardation and back calculate it from that. But it turns out for these solvents, we can actually pull it out from the chemistry of the solvents in saying how much gets absorbed onto organic carbon. In the same way that you'd use a carbon filter to clean up a waste stream, we can calculate how much of it will be sorbed in equilibrium on the organic carbon that's in an aquifer. And so if we know how much organic carbon is in an aquifer, maybe 1%, 2%, 3%, and we know what the fundamental octanol water partition coefficient is, a chemical number, a chemical characteristic that we can get numbers for, we can automatically figure out what KD would be. And if we know what KD is, then we can use it in this expression to be able to figure out what retardation is. If we know what retardation is, then we can figure out what the plume will do. And so not only can we get these information from looking at the field by back calculation, we can also get it for forward analysis by doing something else, which we won't personally talk about next time, but you will experience in YouTube living color on Tuesday. Okay? So that's next week. All right.